All right, guys, first off, I've got up on Canvas is the updated homework sheet. Nothing's really changed with the homework, but just the dates have changed down a ways, right? So I'm going to try to catch up. There's a few sections I can throw out if I want to. So we'll see. I think we could probably, believe it or not, catch up. We missed a few things. So what I want to do today is go over some probability stuff with you guys, because I could tell that the videos I sent links for were actually watched. That's awesome. I saw the numbers ticking up. I'm like, kick ass. You guys are watching those videos. It's the next best thing to actually being in class. So I've got videos going back to like 2011 or something crazy. So, so you could just search my channel for something and see if I explained something better a few years ago or something. You never know. But I still feel like we probably need some firming up with some of the probability stuff, more than likely. Is that right? Yeah, okay. Especially I want to do that handout from when the sub was here. I want to work on that, but let's actually, yeah, that's not a bad idea. It's got exactly the kind of problem I want to do. Okay, let's do that. Oh, also, up on Canvas, I put this was just, I didn't even look at this yesterday, to be honest. I don't know if anybody, I just did this in case anybody wanted to turn their probability homework in and get it graded, since we have the quiz on Thursday, but I also put up here, well, wait a minute. Oh, that's right, it sends it to you. I should put it up here. In the email I sent was the answer key for the practice double quiz, right? You guys with me? So the email I sent over Canvas had the answer key for this. I brought a few hard copies, but I'm hoping, actually considering some people aren't here, maybe I've got enough for everybody that's here. Okay. So this guy here, does anybody need this? So everybody got that? Who's that? Oh. So there's a side that says, that's not the side I want. There's a side that says in class. And that's what the sub was supposed to go over with you, but I don't think you made it very far on this. Okay. So the basic idea of probability. This idea of probability never changes. Okay? So figure out the probability of something. In fact, right now, is anybody in here left-handed? Okay, no. So the probability of a left-handed person would be 0. Has anyone in here been to a different country? 3 people. Okay, right? So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I've been to a different country also. So 4 of us have been to a different country. What's the probability if I pick somebody at random? There's 12 people in here. 4 of us have been to a different country. What's the probability if I pick somebody, they've been to a different country? 4 out of 12. So the basic idea of probability is really simple, and it actually never changes. Even though the formulas get weird, they're always the same idea. A probability is the number of things that match what I'm looking for divided by the total number of things. So if I roll a die, how many numbers could come up? And I'm not talking about a Dungeons and Dragons die, right? I'm talking about a normal 6-sided die. So how many things could come up? 6. Crazy. So what's probably a roll of 1?
1 and 6.
Is the probably 1 out of 6 because I was talking about a 1? No. What's probably a roll of 5?
1 and 6.
1 chance to get a 5 out of 6 total things. You guys with me? What's probably a roll an even number? if I roll a die? Yeah. How many things match what I'm looking for? 2, 4, 6, 3 out of the total number of things that can happen. Are you guys with me? That idea is really, really basic. In fact, it matches exactly what we say in English. 3 out of 6. Math, 3 divided by 6. 50% chance, right? And I always have to tell a story when I talk about probability. My little brother, I love my little brother. He's like worked as an engineer. He's very practical minded. He says, "Do you teach probability, Jeff?" And I'm like, "Yeah." It's like, what the shit, man? It's either going to happen or it ain't. It's 50-50. Everything's 50-50. I'm like, Jim, don't become a doctor. Dear God. I'm about to go in surgery. I'm like, Doc, what's my chances? 50-50. And he puts the thing on me. Oh my God. Right? Are you guys with me? So there's a lot of misunderstanding about probability because people want them to tell them more than it can. If I had a 95% chance of doing something, is it definitely going to happen?
No.
Shit, no, right? So people, there's a 95% chance of this happening and it doesn't happen. And they're like, well, that's bullshit, 95%. It didn't happen. There's no guarantee if it's 95%. If there's a 1% chance of something happening, does that mean it's not going to happen? Of course not. It just means it's really unlikely. Are you guys kind of with me? A little bit? So there's a lot of misunderstanding about probability and how to interpret it correctly. Okay, I like it. So, for example, in a court case, if you are found not guilty, does that mean you are innocent? No, it just means the probability is higher that you are not guilty, that you didn't do it. That's what that within a reasonable doubt, right? That's what that means. Give or take 5%, whatever. Okay, maybe. So, when you have a table like this, since probabilities are based on the total number of things that could happen, the most important thing is to first know how many things could happen. So can anybody tell me, how do I figure out how many total students there are up there? Add them all up. How many total students are majoring in business in this?
92.
Yeah, so to figure out how many are majoring in business, I just add these together, right? 55 happen to be at Grossmont, 37 at Quemont. So 92. And then you just keep going. How many total computer science?
73.
How many math?
9.
Or a little math? How many Grossmont students are in this?
50.
So you can start.
50.
No, a lot more than that. Grossmont students.
126.
Oh. 126.
126. And then how many Quemont students?
That's 50.
That's 50? I like it. Now, one big mistake I see, is everybody cool with that? That's just me totaling up all the various categories. Why does that make sense? Because they're going to be denominators. Aren't they totals of things? And isn't the total number of things, isn't that what goes on the bottom of a probability? Okay, I love it. So this is a classic problem. It's called a contingency table. And you know I'm going to give you this problem on the double quiz and on the final, right? You know you're going to get a little box because it's so perfect for probabilities. Not just that, because it's used in the real world too. One big mistake I see people make, they'll say 126 plus 50, that's 176, plus 11, plus 73, plus 92. You guys follow what I just did? What's wrong with that? If I add these together and then I add these on top of it and say that's the total number of students, what mistake did I make?
Counting everything twice.
I counted everybody twice. You guys see that? But I've seen that often enough, I want to point out that's not the right thing to do. So all you got to do, this is a beautiful check. Whatever these add up to be, these also have to add up to be, because they're both talking about the same group. So thankfully, they both add up to 176. Both ways. Okay. Now, unfortunately, I think that's as far as you guys made it in class. I don't know. I think that's what Maddie said. I can't remember. How many total students are we talking about? 176. So what's the probability? If I pick one person at random from this group, what's the probability they go to Grossmont? Well, how many match what I'm looking for? What am I looking for? Going to Grossmont. So how many match that? 126. Out of 176. I love it. So the bottom will always be the total amount unless I know more. Right? If I don't know shit about the person, how many people could it be? 176. If I knew that person was majoring in math, how many people could I be talking about? 11 people. So the only time the bottom will change is if I give you more information. That's the given idea, right? So probably they take gross score. 126 out of 176. Somebody help me out. What is that? I've got some calculators, by the way. You might need those. What is that? What do you get when you divide those?
0.7159.
Say it one more time.
0.7159.
7159. Beautiful. Kick ass. I do want you to go 4 decimal places because I'm a math jerk. I'm a math person, so I want you to go. There's a bigger reason why I want you to go 4 places, and you'll see when we get to chapter 6. Okay. That's pretty basic so far, I hope, right? That's just making a ratio of the part divided by the whole. So you guys do part B, real quick. Get all the way down to the 4 decimal place answer. Don't say anything, just do it. If you need to borrow a calculator, there's some up here. Oh, sure. We're doing this. Oh, what's your name? Just like you, let's see. Top there. Nice. All right, so who's got that? What's the fraction?
92.
Yeah, there's 92 business majors out of 176 total people. And when you divide that, somebody else tell me what you get.
52.27%.
Say it one more time.
52.27.
27? Okay. So it's a little more than a half a chance, a little more than a 50-50 chance that somebody's a business major. It makes sense. This is a higher probability they attend Grossmont because Grossmont's bigger. It's got more students. Not as many as we used to, but we still have more students. All right. How you guys doing so far? I mean, this probabilities don't require a ton of mathematics. It just requires a little bit of concept, a little bit of what makes sense. So, or is interesting. If I say probably something or something else. So here's what I like to talk about. If I go to a bar, and there's a bar, and there's a bouncer, and there's a line to get in. Are you guys with me? It's kind of a high scale bar. I don't know why I'm trying to get in there, but oh well. So I'm in this line, and I get to the dude, and I'm like, listen, man, can I go in? The or bouncer is the nice bouncer. The or bouncer says, all right, you got to dress nice. No. You got to be rich. No. Or you got to know Joe, the bartender. I'm like, Joe, hey, Joe, I know Joe. And then I go in. You guys with me? He's the nice guy. More people can get in if it's an or. The and bouncer is like, you got to be rich. No. You got to dress nice. No. And you got to know Joe. Man, I don't meet all 3 requirements. I can't get in the damn place. So the or probability will always be a bigger number because or lets more things in. You guys semi with me? Have any of you guys ever applied for a scholarship? Yes? Back in my day, right? Right, kids? Right, walk uphill both ways and bullshit. There was this giant freaking scholarship book in the financial aid office. And you go in, you sit down, open this damn book, and you start looking through scholarships. This is how we did it back in the days when the internet was young, right? And there would be a list of things. You must be a math major. Yes. You must have a GPA of this. Barely. You must be this. You must be this. And the last line, and you must be the son of a Freemason. I don't know. You guys with me? And then like, damn it. Turn the page. So and is more restrictive. You have to meet every requirement. Or lets everybody, it's like, come on in, right? So you got to be a computer science major. So how many people are we talking about so far? 73. Or you can attend Grossmont. And there's 126 people. Now, if I do this, what if I made a mistake? It's sort of a similar mistake to earlier. If I just go 73 plus 126 out of 176, I made a mistake. It's not quite right yet. If I add these 73 people to these 126 people, can you guys see what mistake I've made? What mistake have I made? Twice. I counted how many people twice? 62 people twice, right? This is sort of like voting, right? Some of us hope we could vote twice, but you can't. Too bad. Vote early, vote often, right? No. So, doesn't it make sense that I should do this? But to be honest, there's a quicker way to do it. But in general, right? Do you guys see where that's there? I really want you guys to see. So these 73 people and these 126 people, if I add them, didn't I add this one twice? I added those 62 people twice. That doesn't make any sense. Okay. And that lines up. Do you guys remember what the OR formula is? You guys should have talked about this.
It is probability of A plus probability of B minus probability of A and B. From that.
Yeah, so if A is computer science people, that's the 73 out of 176. B, that's a plus by the way. B is Grossmont students, that's the 126 out of 176. Then I got to subtract any that are both. And how many people are both computer science majors and Grossmont students? 62. In fact, another name for and is intersection. What is the intersection of Grossmont and computer science? Frickin' 62. So that's an awesome thing to remember. Another name for and is intersection. Where do they intersect? How many people are there in the intersection? I really want this OR formula to make sense. Why is there a minus on it? Because if you just add the two together, you might have counted some twice. Okay, I like it. So part D should be really straightforward. Mistake people make is you guys learn the formula for and in the formula. It's so much easier. If I have all the numbers, if I'm able to just count all the answers, all the people, I don't need formulas. In fact, this is the kind of problem I would do to create the formulas. When we did this problem, I didn't know the formula. Well, you guys did, but we didn't have to know the formula. We actually could figure out the formula from what the shit we did. That's different than what we're used to. We did something and then we went, oh, what did we just do? Let's make a formula out of what we just did. So over here, the formula for and is complicated as shit, but I don't need it. What's the probability they're a math major and they're a Cuyamaca student? So how many people are we talking about? They got to be a math major and a Cuyamaca student. That's the mean bouncer. It's going to let less people in. So how many people are math majors and Cuyamaca students? So is this person a math major? These people?
Yes.
Yes. But am I going to count them for this?
No.
Because they're not also Cuyamaca students. So how many people are math majors and Cuyamaca students? 2. Out of what? 176. We're going to talk about the formula for and. But if I'm able to count stuff, I don't need the formulas. I really don't. Which feels different. Every math course you take, you're like, here's the formulas, you better use them. This is an idea. So many things in statistics are just ideas that I don't need formulas. In fact, we create the formulas based on the idea. Really want this to make sense. And then, of course, whatever the hell that is as a decimal. What is 2 divided by 176? Very small. I like it.
0.113.
Close.
4.
Damn it. All right, let me stop for a minute. All right. So probabilities have formulas. There's a formula for or, and, given, all this shit, right? You do not need any of those formulas when I am able to count everything. And here I've given us all the freaking numbers. I don't need any of those formulas. Do the formulas work? Oh, hell yeah. Do they make the problem harder? Oh, hell yeah. Okay, maybe. Because I can always just apply the basic idea. I don't need the formula all the time. And that's the broader idea of mathematics. But you guys are so used to so many courses, here's the formula, here's the formula, here's the formula. That's not the broader idea of mathematics. All right, so here's the freaky thing. So living up to my word, we're going to apply the idea, and then we're going to figure out what the formula is based on what the hell we did. So can somebody tell me, in this problem, part E, we're actually told more information. What do I know about the student in part E? What am I told? What do I know about the student for sure? No. This is what's the probability that they're a Grossman student given they're a computer science major. So what do I know about them? They're a computer science major, right? You guys see that? I'm given this information. You guys with me? So what does that do? Am I talking about 176 students now? How many students am I talking about now? I know they're computer science major. How many people am I talking about? 73. If I know they're a computer science major, I'm talking about those 73 people, and in fact, you could frickin' do this. Frickin'. Really, John, you said frickin'? I did. There's my whole universe right there. Given they're a computer science major, that's all I care about. That little column right there. So now it's going to be out of 73. Now the question is, out of those 73 people, what's the probability to get a Grossman student? Out of those 73 people, how many are Grossman students? 62. How many are Grossman students out of the computer science students? 62 out of 73 is exactly what we just did. Why is the bottom not 176? Because we can throw some people out. I know they're computer science majors, so I can throw these people out. No offense to business. And I can throw these people out. Yeah, screw you, Matt. No offense to them. Maybe? So the only time the bottom won't be the total number is if it's a given. Because then I can throw some shit out. How are you guys doing? A little bit better? Okay. So let's figure out what the hell we just did. Can somebody describe to me what 62 is? Who are these 62 people?
Grossman students.
And?
Computer science.
Yes. So that is the probability of, that's the number of Grossman students who are also computer science people. So let's break down what the hell we just did. This is the answer. Throw that in the old calculator, get the number. I almost don't care right now, but what did we just do? So the given, on the top goes the and on the bottom goes the one that's given. So the probability, and what's this line here mean that you can almost see? The line means given. It's just a little, math people, we don't like to write a lot. Some math people write well, but I really don't like to write a lot because I write worse shit, right? So the little line means given. The probability of A given B. Well, if I'm given B, that's going to be my new denominator. And the only way it could be A is if it's A and B, because B happened. Okay, maybe. So real quick, visually, let me give you a visual. We don't really play much with Venn diagrams, but I want to show you one. You guys have seen this kind of thing before, right? Okay. A given B. What that means is, I know something here happened. Scheisse. I know something in B happened. Yes? Given that B happened. What's the only way that something in A could have also happened? Could it be here? Could it be this little piece, this little hair here? No, right? Where does it have to be? I know something in B happened, so it's the only way that A could have also happened is if it's in here. And of course, what is this piece?
The intersection.
A and B. I like it. So that's where the formula comes from. The only way this could work is if I know that B happens, so that goes in the bottom, and the only things that match what I'm looking for then would be A and B. Okay. A, B. And now we get to something really interesting. So let me ask you this. Let me see what you guys think. Let's say the probability of A is 0.7. Right? Maybe there's a 70% chance that you'll pass the final, right? Kind of like thinking to yourself, yeah, I think I got a 70% chance. You guys with me? So we all sort of do this. We don't necessarily put a number on it, but you all have a feeling about how you're going to do, correct? Right? And you're not sure how to interpret it. Sometimes I'm worried if I'm overconfident. I'm like, damn it, I got to. Okay. You also shouldn't be sweating too. So let's say you think there's a 70% chance. What's the probability? What do you think the probability you're going to pass the final, given that you study, every week? Given that you get a tutor to help you, do you think it would stay the same? Do you think the probability you would pass would stay the same if you start going to see a tutor? What should happen? It should go up, right? So let's say maybe it's 8%. So would you say that the chances you pass the final exam, are they dependent or independent from getting tutoring? Does getting tutoring affect the chances you pass the final? Yes, because the number changed, right? So it was 70% and now it's 80%. So this would be an example of two things that are dependent. So for example, what's the probability you can get up early the next morning? Is there anything that depends on? You got to get up early the next day.
I have a reason to.
Yeah, motivation. If you're not motivated, you're not going to get up early, correct? So the probability you get up early is dependent on how motivated you feel, correct? If you got to get up early to get to an interview for a job that you've been working for your entire life, I think you're motivated, yes? So they're probably going to get up early, goes way the hell up. If you got to get up early because your next door neighbor that you don't like said, hey, if you got time, can you come over and help me move this washer and dryer? Are you as motivated? No, in fact, it probably might go down then. You're like, screw it. Maybe, right? I don't know. It depends on what kind of person you are, I guess. Obviously, I'm an asshole, but I'm like, screw this guy. All right. You guys kind of with me? So dependent does not mean it can't happen without the other thing. Dependent means the probability changes. So what I'm saying is, in order to be independent, for A and B to be independent, the probability of A given B has to stay the same. Now look what this says. Given that B happened, does A give a shit? No. If I know B happened, did the probability of A change? This says no, it stayed the same. Do you guys see that? I really want this to make nothing but sense. If B happens, right? Let's say that somebody across campus sneezes right now. Does that affect us at all? No. You can talk about butterfly effect. Let's not go there. Right. So somebody across the campus sneezes. So that is, we are independent. Anything we do is independent from somebody sneezing across the other side of campus. Are you guys in agreement with me? A little bit, okay. You guys kind of with me here? So that's what independent means. Something happening does not change the probability of something else happening. So if the probability of A given B is the same as the probability of A period, they are independent. So let's look at this. Are being a Grossmont student and being a computer science major, are those independent? Well, what's the probability of being a Grossmont student given computer science major? Didn't we calculate that?
Yes.
Can somebody tell me what the decimal is for that?
8493.
8493. Compared to what's probably that somebody's a Grossmont student?
Is that 126 or 176?
That's 7159, right? Now, real quick, I'll tell you this. I like to do this. When I ask you this question, and you know I'm going to ask you this question, you will have already done the work you need. So how do you check to see if two things are independent? You look at the given probability of this given the other dude versus the probability of this guy by itself. So if I know somebody's a computer science major, does the probability they're a Grossmont student change? What's the probability they're a Grossmont student not knowing shit?
71%.
If I know they're a computer science major, does that change?
Yes.
In fact, it goes up. You guys with me? Why is that an important kind of probability to calculate? Because if the probability that I do well in the SAT increases if I take some SAT prep course, then I'm going to take the freaking SAT prep course, right? If I really want a high SAT. Are you guys with me? So it's important to know what happens if we do this. In fact, that's like the basis of almost every damn thing. Should I do this? What's that going to do for me, right? You guys kind of follow? So if you know more languages, could that increase the probability you're hired somewhere? So does that increase your motivation to learn more languages then? Yes, right? You guys kind of follow? This is the basis of what we always do. We always do these freaking conditional probabilities, these given probabilities. Given that it's 4 o'clock, should I hit the road and try to go home? No. I'm going to stay here for a couple hours because I'll be in traffic for a couple hours if I go right now. You guys understand what I'm talking about? If you're in a certain area at a certain time in San Diego, you just are like, well, we missed our time. We missed the window. Let's just stay here. Have you guys ever done that? I mean, when I first moved here, I learned very quickly what time. Oh, screw it. I'm going to stay here. I don't want to be in that. No. Okay, I'm sorry. So I just want to point out, we do these probabilities all the damn time, just not this detail. But we still do them all the time. Okay. Woo! So this is one kind of problem, is this contingency table. And you have to let it be pretty straightforward. It's just a bunch of ratios. Part divided by whole. Right? Okay. So let me ask you a couple of bonus questions. Can you guys take a minute? Don't say anything. Can you figure out what's the probability somebody is a math major given they go to Cuimaca? Don't say anything else. Cool. So don't say anything yet, but let me just help out a little bit in case you're having trouble. What do I know about the student I'm talking about? Given they go to Cuimaca. So I know they go to Cuimaca. Don't say anything. So I know what the bottom is going to be. Out of those, and your math. So what's going to be on the bottom? Yeah, now we're talking about 50 people. I know they came from Cuimaca. So there's only 50 of those. Out of those people, how many are math majors? 2. Now let's try this. What's the probability they're a Cuimaca student? Good Lord, John. Given they're a math major. That's not the same question, right? Don't say anything. Another way to say this is, amongst all the math majors, what's the probability I get a Cuimaca student? That's another way to say this. In fact, that's how the homework very often puts it, is the word among. Not among us. There are some things that are sus about some of these problems. But, how many people am I talking about now? How many people could it be? What kind of person do we know this is? They're math majors. So how many people could it be? 11. Out of those 11, how many are Cuimaca students? 2. See how these are very different probabilities, yes? Yes. Let me stop for a minute. Okay. Okay. So the word for that is, this is given. That's just the word for that symbol. But this probability is called a conditional probability. On the condition that they're a Cuimaca student, what's probably their math major, so forth. Okay. Number 2, 2A and 2B. I feel pretty comfortable saying this. If this is not true, don't take this wrong. But 2A and 2B should be easy as shit. Do 2A and 2B. Let me check in. I think somebody just came in. Everybody's got this handout? This is from the day the sub was here? You have this handout? Do you need it? You got it? Oh, you need it. Okay. I really hope you guys agree with me that A and B should be really easy. How many people are in this house? 21. Probability that are a Democrat. So out of 21, how many are Democrats? 7. So this is the basic idea of probability. 7 match what I'm looking for out of 21 total. What's 7 out of 21? 1/3, which is 3. Now again, I've rounded it. So in general, I want probabilities rounded to 4 decimal places as a decimal. You could make that into a percentage, and then it would, good Lord, Jeff, what number is that? Then it would be 33.33%. That's up to you, this one. Yes?
For like repeating ones like that, can we just put 3 with the bar?
That's fine.
Do you want to write it up?
Oh, I see. That's fine. That's even more correct, so I'm happy with that. But in general, if you're going to round to 4 decimal places, yeah. And then what's part B? Same idea, right? How many are Republicans? 12. So that'll be 4 sevens, which I believe is 0.5714. It's a little weird that I think I have that memorized.
I mean, yeah, it sounds right.
Sounds good. Is it 5714? I'm a math guy. You never know what the shit I'm gonna know about numbers. I know all my divided by sevens.
6 episodes.
Well, I don't know them like that. But give me a second. 0.85 something. Yeah? Okay. Okay, so those two, very straightforward. You gotta love those signs. You know the basic problem about here's a bag and there's 4 green marbles and there's 5 blue marbles. Those kind of probability questions, easy as shit. Just add up how many there are total, that's the bottom, and then if I say, what's probably get a green one? Well, you put the number green on top. Let that be easy as shit. And then immediately we get really freaky here. Right? Well, here even, yeah. So now we're talking about picking 2 people. So, we got to talk about how to do this. This is going to be the AND equation, which we haven't had to use yet. So let me do, I'm going to do 2 quick examples. What time is it? I want to see how quick it is. One is silly and one is serious, right? 2 quick examples for this. Let me start with the serious one. Do you guys, this is really unfortunate. I hate that I have to say it this way. Do you guys know how many times the space shuttle blew up? Obviously not the same one, but
Like 3.
twice. Once when I was a little kid, I lived in Florida. We would always go out and watch the shuttle take off because we could actually see it off in the distance. For some reason this day we didn't go out. And then over the loudspeaker, I'm in my English class, sitting in the first row, of course, because then I can get out the door quick, right? And over the loudspeaker, they're like, the space shuttle, we're sorry to say, it's exploded, everybody's died. And I just started crying like hell because, I was always a geek and I'm totally into space shit. So I'm just crying. So I'll never forget that. It's emblazoned in my brain, right? I don't mean to be bringing us down, but that just happened. And everybody knows this, correct? You guys know about this, okay. And of course, the second time was it was coming back in to land, and it made it up fine, but so many of the heat shields had fallen off that it basically exploded when it hit the atmosphere and started heating up. It exploded, and they were finding little bits of it all across America, all across Texas and all that. You guys, again, great job, Jeff. Let's talk about people dying and everything. Great. Way to go. Pick us up. So happy you're back. Now, stay with me. There's a point to this. Do you guys know why the first shuttle exploded?
I don't know, grounding error.
Okay. It's a really interesting, and again, I know we're talking about people who lost their lives, but it's really unfortunate because they were just so freaking arrogant. We had done it so many times, like, oh yeah, this is it. It's just like crossing the road. Just throw them up there. There, in the fuel line, there was these valves called O-rings. Yeah, Jeff. What their job was to make sure that the fuel was going in the right direction. It kind of makes sense it would be bad if it was going in the wrong direction. That could lead to problems, and obviously it did. So let's say, for the sake of argument, that the probability that one of these failed, let's just say it's 1 out of 100. Obviously it was much less than that, but just to make this easier to think about. Are you guys kind of with me? 1 out of 100 chance that one of them will fail. So why would they want to put several of them in there then?
Because it's exponentially less likely.
Yeah, sort of like if you live in a bad neighborhood. The worse the neighborhood is, the more locks you're going to have on your door. Do you guys agree? I've certainly grown up. When I grew up, we lived in several bad neighborhoods. There were several locks, and they were all different kinds of locks. Because you're like, if you're going to break in my house, I want you to earn that shit, right? So why would I put several locks on the door? Why would we put several O-rings in the fuel line? Because if one fails, you still have the other ones, correct? If one lock is unlocked, you still have the other ones. If you really got to get up in the morning, does anybody do this? Set 2 alarms? Because if one doesn't work, then you're hopeful the other one will. And of course, one time they both failed, and I was late, and it was fantastic. It was great. It was a final. It was great. It's a great way to start a final, is to be 20 minutes late. Yeah. So watch this. Obviously, I can't add. So this would be 0.01, this would be 0.01, this is 0.01. So what's the probability that all 3 of these fail? It wouldn't make any sense if I added them together, because then the probability goes up. So this is 1 out of 100 times this one fails, correct? in order for these two to both fail, this one's got to fail given that that one fails. So 1 out of 100 of these times, both of these fail. And then 1 out of 100 of these times, all 3 fail. So you end up multiplying the probabilities. Now normally when you multiply two numbers, it gets bigger, correct? 2 times 7 is 14. Ooh, that's amazing, Jeff. Good job. Yeah. But when I multiply two numbers that are less than 1, you guys all know this. What's 0.6 times 0.6? 0.36. Right? 6 times 6 is 36. Move it back twice. When you multiply two numbers that are less than 1, the answer gets smaller. Right? So this would be 1 out of 100 times 1 out of 100 times 1 out of 100. So and basically means multiply, or basically means add. You guys semi with me? Or basically means add, and basically means multiply. Okay. Now, so that's kind of setting this up. My silly example is, let's say I wanted to join a fraternity. And they do some mild hazing, nothing that would get them closed down. There's been several stories about some weird ass shit, but in this case, what they do is I have to walk down this hallway, and every third step, somebody slaps me on this cheek, right? And every fifth step, somebody slaps me on that cheek. You with me? So there's a 1/3 chance they're going to slap me here, and there's a 1/5 chance they're going to slap me here, correct? So if I'm walking along, how often will I get both? Think about it for a minute. Every third step, slap. Every fifth step, slap. Is there ever going to be a time when I get both?
15.
Holy crap. Thought part of my head came off. Right.
15.
Every 15th step, correct? Isn't that 1/3 times 1/5 is 1/15? 1 out of 15 times, both. Still multiply, of course. I multiply. And this cheek and that cheek, 1/3 times 1/5. Okay. So, let's look at this. I know I haven't written a formula yet because the formula is going to come out when we get here, to be honest. But we're going to actually do the problem and then we're going to figure out the formula. So if I want to know, this is really huge, the with replacement. What that means is I pick somebody and then I put them back in, which is hilarious to me for this problem because I take them out like, oh, thank God, thank you, we got to go back in. Right? And again, I don't necessarily believe in haunted houses, but this is whatever. Right? Watch those ghost hunters and they haven't found them. So, that first person, what's the probability we pick an independent, somebody who's independent? They're not Democrat or Republican or Whig or Communist or anything.
2.
Out of?
Oh, 21.
Yeah, so any probability's got to be less than 1, correct? In the end. So there's a 2 out of 21 chance that they're an independent. So I take them out, they're like, oh, thank you, and then I shove them back in the house. I replace them, I put them back in. It's an and, correct? So that means times, what's probably the next person is a Republican? 12 out of 21. Then I just got to multiply those together. Let's see, it's like 0.056. I don't know.
0.054.
Damn! So, I should retire, sorry. 0.54. 4. So can you guys do part D? And do you see how in part D it doesn't say and? Because the English language is like that. But if we select 2 Democrats, that means I select a Democrat and then another Democrat, right? So there's an and in there. So watch how this works. This is so cool. When you have, I know I just said it. An and problem, I have 2 things, right? One pick times the other pick. So what's probably the first person is a Democrat? first person I pick is a Democrat. What's that probability? We actually already figured it out.
7 or
7 out of 21, right? This probably is a Democrat. 7 out of 21 chance. And then I throw them back in the house. What's probably the next person is a Democrat.
21.
Still 7 out of 21, correct? Okay. So when you see an and, there's a part of this is, but if none of the numbers change, do you see how I keep putting them back in this problem? So the next one is going to be a little different because that's where I don't put them back in the house. If I have an and, I'm going to multiply probabilities. So if I picked 3 people out of the house, I would just have times one more thing. It just kind of keeps going. So the second person to be a Democrat is a 7 out of 21 chance. And that's 0.111. Okay. So or basically means add, and basically means multiply. Okay. So what happens if I don't put the person back in before I select the next one? So let's see. I still have 2 people, right? I'm picking 2 people, so I know there's going to be one person and multiply the next. So everybody's in the house, and I pick somebody at random. What's the probability the person I pick is independent? Well, it's still going to be 2 out of 21, yes? And then I let them go. I say, go home, and they're like, all right. Or, you don't have to go home, but you don't have to stay in the freaking haunted house. So I let them go. What's different now in the house? There's only 20 people in the house now, right? You guys with me? So if I pick somebody and I don't replace them back in, I don't put them back in, I let them go, aren't there only 20 people left now? So what's the probability I get a Republican now? How many Republicans are still in the house? Because I took an independent, right? So there's still all 12 Republicans out of how many total people now? 20. So if I had a third person I was going to pick, what would the bottom be? If I had one more thing to do, if I had a third person I was going to put here, what would the bottom be? So why is the bottom 20 here? Because this person I let them go. And this person I let them go. So what's the bottom going to be here? 19. Isn't there one less person? Every time I pick somebody, isn't there one less person in the house? So I could say, if we select 18 people, well I couldn't because how many people? 20. If I select 18 people, I could just have a row of 18 fractions. And he says 21, 20, 19, 18, 17, 16, right? Because every time I pick somebody, I'm like, get out of here, get out of here, get out of here, right? And I'm throwing these people like, get up. Okay, maybe. Now I got that scene, Quicksilver running into that. And then whatever that is, what is that? Let's see, 1/10 of 3/5, 0.059.
5, 7.
Damn, I'm always too off. 0.571. So now, if we're going to select 2 Democrats, first person is kick-ass because nothing's happened yet. So what's the probability the first person is a Democrat?
7 over 20.
Yeah, that doesn't change. 7 to 20. Then I let them leave. I let that person go. How many people are in the house now? 20. How many Democrats are still in the house? Who was the first person? First one was a Democrat. I let them go. So there's one less person, but there's also one less Democrat. So what's probably the next person is a Democrat? There's 20 people in the house, 6 Democrats. So it'll be 6 out of 20. So if I said, what's probably I get 5 Democrats, that'd be 7 out of 21 times 6 out of 20 times 5 out of 19 times 4 out of 18, as many, whatever I just said, right? So why didn't these bottoms change? Because whenever I pick somebody, I put them back in. Why did these values change? Because in this case, I let them go. So of course there's less and less and less and less things in the house, right? Maybe. Okay. So what is that going to be? 1/3 of 3/10 is 1/10, so 0.1. 0, 0, 0. So, what we just did in the formula for and, in general, so this was, let's do this one. This was the probability of let's do this, of independent and Republican, correct? That first problem? And how did we do it? Didn't we do the probability of independent times, now, can somebody tell me, is this really the probability of Republican? No. What's the probability somebody's Republican? Well, we did that up here, 12 out of 21, right? So what the hell is 12 out of 20? That is the probability somebody's Republican, given that I already picked an independent. So I think you guys are cool with the fact that if I'm seeking people out, obviously the total number is going down. That means the probability has changed because something happened. So that's a given. So given that I picked an independent, that is why this freaking number changed. Okay, meta. So in general, the probability of A, holy crap it happened. Probability of A and B. This is the probability of A times the probability of B given A. Or probability of B times probability of A given B. Actually works either way. And let me show you algebraically why that's true. Well, you guys look so excited. You're like, oh, I'm so happy you're back, Jeff. Oh, thank you. So much statistics in that. Can somebody remind me what the probability of A given B? What was that? Now, algebraically, if I want to solve for the probability of A and B, can't you just multiply that up? Would I just multiply both sides by peanut butter? By P of B? You guys see what I'm saying? Just multiply that up. Isn't that the second equation up there? If I multiply this up, isn't it just this? So where the shit does this one come from? Well, that comes from probably B given A. Doesn't it also have A and B in it? And if I multiply the P of A up, I'll get this one. So in your homework, they're going to ask you to calculate an and. There's actually two ways to do it. So which way do you pick? You pick the way where you know something. If you don't know this, you don't know this, you can't do it this way. You have to do it the other way. Okay. So it's kind of, that one is the hardest one because there's two ways to do it. Because there's two ways the and shows up. Okay. So obviously, you can start adding these probability formulas to your formula sheet. And of course, we'll make a formula sheet specific for the, actually I have to do that today because it's this Thursday. I think we got everything. Let's see. So what could be on your formula sheet for this coming up test? You can have the given. You can have the and both ways. And you can have the or. You can have all that on your formula sheet, right, for this Thursday.
Do you use the same formula sheet you use?
Yeah, you could just keep adding to it if you want to. Or you could bring a specific one. So like on the final, you could bring like 7 formula sheets. Does that make sense? By the way, if you lost points on the formula sheet, which people did, why would you lose points on the formula sheet, Jeff? Because they told you would. because you had too much information on there. You can only have formulas on there. Obviously, rewrite those, right? Don't bring those back, because then you'll lose points again. So rewrite it, everything's good, right? Okay. Now, so now that we have these formulas, let's do this last problem. This is the first place that I really, really need the formulas, because I didn't give us anything to count. Now, I do like to use, I don't always do this, but I do like to infuse into my tests and quizzes actual real-life data. So this is a real thing that happened. You guys understand what I'm saying? So to be really, really honest, the way that they worded the survey sort of led to people saying this when they didn't really think this. But it's still concerning, right? Some of them actually believe this. So there are some people out there who think that chocolate milk comes from brown cows. That's the reality we're in. Fortunately, I think probably it's gone up. I don't know. There's a good chance. Anyway, so did I give us numbers to count? No, I just gave us probabilities. Damn it. So, help me out. When you see a problem like this that gives us a probability, you got to start coming up with variables and describing what the probability is. So what do you want to call? So what situations do we have? Americans think that chocolate milk comes from brown cows. What letter do you want to use for that? A. It's crazy. That makes sense. So the probability that Americans think that chocolate milk comes from brown cows is what? 7%. 7%. I want to do part C first, because part A and B are a little bit different. Look at part C. So we know that the probability that Americans think chocolate milk comes from brown cows is 0.07. Let's do part C first. If we also know that 4% of Americans think that chocolate milk comes from brown cows and that Brussels sprouts are the best vegetable, right? So what letter do you want to use for people that think that Brussels sprouts are the best vegetable?
C.
That makes so much sense.
Does it?
No, let's use B.
I was going to say C, so we use B for that.
Say again?
Yeah, I got that.
Thank you. Well, I gotta be careful. So B is people that think Brussels sprouts are the best. You with me? I really was missing. So what symbol would I use for 4%? Probability of what equals 4%? Not the probability of B, right? But the probability of, bless you, thank you, A and B. So this is going to happen a lot in the homework. There's at least 2 problems, maybe 3 or 4, where you have to kind of give symbols to the numbers they give you. So those 2 things, the problem just tells me these 2 things. I don't have to calculate them, they just tell me these 2 things. Now what probability does it want me to find? Can somebody tell me in symbols the probability they want me to find? Find the probability that an American likes Brussels sprouts, given that they think chocolate milk comes from. In letters, what would that be? I'll get us started. It'll be, so the question is, what's the probability of, what goes in there? What do we call American likes Brussels sprouts? B. Given they think chocolate milk comes from brown cows. A. So probably a B given A. That's the question, correct? So many of these, it works just like normal mathematics. And, you know, what am I talking about? Probability is normal. But it works just like algebra. We have to identify, okay, they gave me this number. Which variable is that number? Which variable is that number? And then they ask me a question. What's the formula for the question, correct? So in this case, they told me P of A. They told me P of A and B. And they're asking me for this. What's the formula for this? And again, you can look back at your little formula sheet. Look at that, look at that, look at that. It's the and divided by the given. Do I know these 2 things? Yes, I know, it's gonna be 0.04 divided by 0.07, which again is one of my favorite numbers, 571. So this feels a lot like algebra, except our variables aren't just x and y. Our variables are p of a and b, p of a given b, maybe. So again, the only kind of problem that you need the probability formulas for is this kind, where I don't give you all the numbers to count. I didn't give you any numbers, I just gave you probabilities. You have to use the formulas. For the first problem, I didn't need formulas for any of this. I didn't. We could do all of these without any freaking formulas. Woo! All right. Now, let me see if I can truncate this explanation here. How many Americans are there?
A lot.
There's a few, right? It's a few Americans. What is it, 330, 340, somewhere in between 330 and 340 million? I think we passed 300 million in 2008. That feels right. Anyway, it doesn't matter. Who cares? So, a little trivia for you, kids. Right? There's 300 and let's just say 330 million Americans. You with me? There's a lot of freaking. This is talking about a huge population, correct? Let's see if this. How can I explain this really quickly? I don't have to do this shit. Was this a very big population?
No.
21 people, right? You guys help me out real quick. What is 12 divided by 21? It's 5714, yes? Right? What's 12 divided by 20? 12 divided by 21 is 0.5714. What's 12 divided by 20? 0.6. That's a relatively big change, isn't it? From 0.5714 to 0.6. It's like a 3% change. Are you guys with me? Can somebody help me out? What is 12 out of 20,000? Help me out. Well,
6 over 10,000, 3 over 5,000.
let me point. Let me think for a second. 0006, is that right?
Sure.
Help me out. Is that true? Help an old math teacher out.
Yes.
Now, what is 12 divided by 19,999? That's like if I took one person out, right?
That's that number plus a 0003.
Sorry?
It's the 0.006 with a 0003 after.
No. No.
Is it not?
No. It's,
It's something.
yeah. Yeah, it's just 0.006. By the way, real quick, you see on the calculator it says this? When you see that, we're going to see this a lot because some probabilities get very tiny. This means times 10 to the little e, dude. Do you guys remember scientific notation? And if you don't remember something, all it means is whatever number that is, you want to go, if it's negative, you want to go back 4 places. So it'll be back 1, 2, 3, 4. So it should be 3 zeros. Yay.
I was saying for the next one.
Oh, okay, gotcha. I'm sorry. Yeah, 12 divided by, if I lost one person, it barely changes at all. So, all right. The long and short of this is, I've got 4 people I'm picking, correct? And I want the first one to think this is true, and the last 3 don't. So I got 4 people, and they're going to be multiplied together because it's and. What's probably the first one thinks chocolate milk comes from brown cows? 7%. 0.07 goes here. I don't have to change the denominators because the denominator is 330 million. So I can just keep the pure percentages. What's the probability that the last three, what's probably this guy does not believe that? If this is a 7% chance they do, what's probably that they don't? 7% chance that they do think so, what's probably they don't think so? If there's a 10% chance it's going to rain today, what's probably it's not going to rain today? 90%, yes. 10% chance it will, 90% chance it won't. So there's a 7% chance they think this way, there's a 93% chance they don't. So the first guy is a 7% chance, and the last three are a 93% chance. And now you just multiply that stuff together. 0.8, 0.7, 0.49? I don't know. That's not right, but it's close. Well, it's like 0.51.
0563.
What is it?
0563.
Oh, yeah, I left that 0 out. 0563. So very unlikely to have exactly that happen. Okay. I think, let me think. Yeah. Okay. Yeah, this is perfect. I think I actually want to talk about chapter 4 a little bit first, and then we'll do this, because to be honest, this is going to make a lot more sense once we've done a little bit of chapter 4, believe it or not. It's actually a little bit easier to explain. But real quick, if I thought that at least one person in here enjoyed my lectures, right? If I said at least one person in here likes my lectures, what's the opposite of that? Which really a good way to think about opposite is, how would you show me that I'm wrong? The only way to show me that I'm wrong, and I love how a lot of you guys are like, nobody likes your lectures. I'm just so happy you let me say that. So the opposite of at least one does something is nobody does that. Does that make sense? How do opposite probabilities work? So just like I said earlier, the probability it's going to rain is 10%. So what's probably is not going to rain?
Is 100% minus that.
Yeah, 90%, the rest, right? 100 minus that. Are you guys with me? If I did it in decimals, the probability something was 0.2. It's probably not that, would be 0.8. 1 minus that, correct? So, the probability of probability of not A is 1 minus probability of A. So the probability of at least 1 is 1 minus probability of none. And at least 1 happens so often, that's why I made a little shortcut to figure it out. And to be honest, this works for more than just at least 1. Let's just stick with at least 1 right now. So this one says, let's probably at least one of them thinks chocolate milk comes from ground cow. So probably of at least 1 thinks that is equal to 1 minus probably that nobody thinks that. And the probably nobody thinks that would be the first person doesn't think that times the next person times the next person times the next person. The only way that nobody could think that is if the first person doesn't think it, and the next person doesn't think it, and the next person doesn't think it, and the next person. That's a 3 there. So then you just throw that in the old calculator. 1 minus 0.93 times 0.93 times 0.93 times 0.93, which would be about 0.3, I think.
0.2519.
Darn it, what was 0.25.
19.
So if you see a probability of at least 1, you could just do 1 minus the probability of none. Why would it suck? It would so freaking suck to try to do this directly. Because how many ways could there be at least 1? If I have 4 people, what does at least 1 mean? It could be one of them. Well, how many ways is it could be one of them? It could be the first guy, or the second guy, or the third guy, or the fourth guy. I'd have to calculate all those probabilities, or, right? They're ors, so I'd have to add them up. But what's at least one mean? It could be one person, or it could be two people. So it could be these two. It could be these two. It could be these two. It could be the first and the last. It could be the first and the third. It could be the second and the fourth. Holy shit! I'd have so much work to do. I'd much rather. What's the only way that nobody could think that way? The first guy doesn't, the next person doesn't, the next person doesn't, the next person. There's only one way. There's only one thing to calculate then. So any freaking time I ask you a probability question and the opposite probability question has less work to do, hell yeah, I'm going to do that shit, and then I'm going to do 1 minus that, because that'll answer my question. Maybe? Since the probabilities is, the probability something is 1 minus probability the opposite, if the opposite has less work, I'll just do that and do 1 minus that. Maybe. Okay, and again, I'll do some chapter 4. I'll show you this in a different way, and then we'll call it a day. Okay. So, just to remind you guys, on the, actually I have some copies of this. I don't have enough for everybody, but I put the answer key for the practice quiz up on Canvas. Is anyone not able to print them out for themselves? And I'll give you a copy. Okay. And if more people want some after that, I'll give it to you. I'll give it to the dude. Oh, okay. Thank you so much. Yep. Anybody else? Okay. So now I'll just open up to anybody who wants one. This one I actually typed up so you can read it. Isn't that crazy? Okay. And then there's more here if anybody wants one. All right. So on Thursday, the probability quiz will obviously not be this, but it will look like this.
Would you ever put at least 2 or no?
Yeah, all right, I'm glad you asked that, because I was about to say it. If it was at least 2, it would be 1 minus the probability of none minus the probability of 1. Because at least 2, what's the opposite of at least 2? 1 or none. Does that make sense? And again, so, okay, I like that question, but I wanted to hold off on it because it gets a little murky, and we see at least 1 much more often than we see at least 2. Okay. Let's see. All right, we got a little bit of time. So I'm just going to do, I'm sure some of you guys are like, well, I don't want you to be sick, Jeff, but can you add one more day? Let's talk about chapter 4 a little bit, because it actually is going to illuminate some of what we did today, I think. Can you turn the light back on back there? Thanks, man. Let's see. Yeah. Cool. Good. First try, man. Let's go. Probably that was 1.5 weeks. Okay. One reason why I put chapter 3 as its own thing, and I have kind of like a double quiz on chapter 3 alone, is because chapter 3 is a weird little section. It's its own little thing. We're going to use some ideas from it throughout the class, but this is not a probability class, right? This is a statistics class, so it's a little bit on its own. That's why I give it its own little double quiz and blah, blah, blah. By the way, double quiz literally means it's about twice as long and it's going to count twice as much as a normal quiz, right? I used to call it mini test, and that freaked people out, so I just call it double quiz. You guys know what I'm talking about? There's a double quiz this Thursday on chapter 3. It's on the updated homework sheet. It was supposed to be, I think, last Thursday, if I remember correctly, but of course, things happened. So now we're here. Okay. Now, all right. So let me just lay down what I'm about to do. What I really try to do with a lot of mathematics, and I'm sorry today's a lot of lecture, but I just got a shit ton to kind of catch up on. Next time we're going to do some more group work on some of the stuff we're going to talk about right now. I like to try to explain, based on stuff we've done before, what we're doing now. So we all freaking know how to calculate an average of a list of numbers, correct? Okay. So real quick, if my list of numbers looked like this, what did I say? 3, 1, 2, 3, 4, 5, 6. So I need 4 more. You can do it, Jeff. Let's do. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. All right. I just want to make it pretty straightforward. If I asked you to calculate the average of these numbers, you would go, oh, thank you, right? How would I calculate the average? What do I do? We'll say this is a population. Add them all up. So what's a smart way? Isn't there a lot of repeats?
Yes.
Okay, so one smart way to do that is there's 2 1s, there's 3 2s, there's 4 3s, and there's 1 4. Divided by 10. Now, I really want you to understand. What I'm doing right now, what I'm about to do, is I'm about to calculate this a different way to show you the basic idea behind chapter 4. And then I'm going to tell you why we need a new way to do things. Because right now you're all like, well, that's easy as shit. Why would I do this a different way? Because what if there were 10 million numbers? Do you want to do it this way? No, right? So what if the population is stupid big? Is there a shortcut way to get the average? Because I don't want to add up 10 million numbers, unless you want to. And then I will give you 10 million numbers. Right? Okay. So couldn't I, this is the, what I'm going to call the old way. It's actually not the old way, but, okay. Shit, I need a wide angle lens for this, okay. So what's the old way? The old way would say, when I get 2 plus 6 is 8, plus 12 is 20, 24 over 10. 2.4, right? Done, yes? And again, if I only have 10 numbers, yeah, I'm going to do it this way, yes? But what I'm about to do shows the idea behind what would I do if there were 10 million numbers, for example. I don't want to do it this way. I don't want it, right? I want a better way. Okay. So watch this. Isn't this, instead of adding first, couldn't I divide first? Isn't this 2 tenths times 1 plus 3 tenths times 2? Mathematically, that's, who gives a shit, right? Math is kind of like, whatever you want to do, human. Yeah? You guys all with the math up there? Now, right now, you might be like, why the shit would you do that, Jeff? You already got the freaking answer. Okay. Because again, what if I had a big ass sample? Isn't this 0.2 times 1 plus 0.3 times 2 plus 0.4 times 3 plus 0.1 times 4? Whoop-de-doo, right? But what does 0.2 mean? What percent of the numbers is 1? 20%. 20% is 1. 30% is 2s. 40% is 3s, right? And if you do this, what do you get? 0.2 plus 0.6 plus 1.2 plus 0.4. Not surprisingly, you still get 2.4. Because the math didn't give a shit, right? So, you're still 11. Right now, you're like, either you're going, I lost this guy the minute he started talking, or you're going, whoop-de shit, I already got the answer. So, here's what this would look like. Couldn't I write this like this? Yeah, could. It sort of looks like a frequency or relative frequency distribution. So I can say 1, there's 20% are 1s, 30% are 2s, 40% are 3s, and 10% are 4s. So then to figure out the average, And again, you can imagine this would be like list 1, list 2. Now tell me real quick, based on what we just did, what would we do with these numbers to actually get the average? When I multiply x times p of x, and then how would I get the average? I would just add that shit up, right? So I'd sum up the x times p of x's, and that would be the average, and I'd still get 2.4. So now I'm sure you guys are still like, holy shit, you took something that we did in like 5 seconds and you did this to it. Good job, Jeff. So here's the final thing. Okay. Here's the final why the hell we do this. What if I had a list of numbers where I want this to make all the sense in the world. I always do. 571 out of 1,000 were ones. So I have 1,000 frickin' numbers. I have a list of 1,000 numbers. And there's a bunch of repeats. In fact, 571 out of 1,000 are ones. Oh, this is going to suck, Jeff. I got to make sure it adds up. 192 of them are twos. What do you got, Jeff? 78 of them are threes. Now, what do I have to be careful about? This is the last number. And now these have all got to add up to be
1,000 or 1.
1, or close to it in case there was rounding. What do I got so far? I don't know. 0.27, 0.841. I think it's 0.159. Is that right?
6.
No, it can't be 159.
6.
27. Oh, it's got to be
741.
259, I think.
Yeah.
No, not 25. Yeah, 259. Okay.
259.
Somebody double check. Somebody help me out?
Yes.
Add these up.
You're good.
You got it? Okay. Math on the fly. Yeah. Yeah, I really want you to understand. If you wanted to make this into a list, wouldn't it be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 571 times? 2, 2, 2, 2, 190. Do you want to do that? Shit, no. So, we're developing a formula if they give me the data like this. I don't want to do it the old way, because then there's 571 ones and there's 192. I don't want to do that shit. We now know what to do. We take the x's times the p of x's. Yes?
I lied. It's 159, not 259.
It is 159. I should have went with my first. Why did I think it? Oh, because of that. 27. That is 8. So that is okay. Thank you. Okay. All right. What did we just do? What should this be?
1.
It should be 1 or close to 1 in case there was rounding. Okay, I love it. Let me stop for a minute. I really want you to understand. Do you understand what so I started with a list of 10 numbers, and I could write it like this. There's no way in hell you would want to do that if I just gave you a list of 10 numbers and said find the average. There's no freaking reason you would do this shit. Are you with me? But if I do that, I can then see what math to do if they give me data like this. Now I know the math to do. I multiply these. Oh, here we go. Oh shit, Jeff. Yeah, that was not too bad. 2, 3, 4.
Yeah.
0.636.
Yeah.
Yeah?
Yes.
Look at me go. Using my one skill. Yay. And then how do I get the mean? What did we figure out just a minute ago? How do we get the mean? What did we figure out? We just add them all up. So here's another formula for the mean. And again, so I want to show you something kind of interesting. You add up the x times p of x's. So if you add all these up, and by the way, before I do that, somebody might have already done it. What's the heaviest weighted number? Do you guys understand what that means? Which number is the heaviest weighted one? Which one occurs the most?
1.
1. So the average should be pulled towards 1. So if I had to guess what the average was, I would say 1.4. So let's see, what is the average? Yeah, add all these up.
1.825.
All right, so I was off, which is fine because I'm just a human. Real quick, what's the average of 1, 2, 3, 4? Isn't it 2.5? Right? If you just average 1, 2, 3, 4, you get 2.5. Why is this average less than 2.5? Because there were a shit ton more ones than anything else. So of course the average is going to be lower. So you can kind of tell ahead of time what's the heaviest weight. And I like to call it the heaviest weight, not just because we call this a weighted average, but because it's sort of like gravity. This is the heaviest weighted thing, so it's going to pull the average towards it. So the average is a little lower than it would have been. Okay, maybe. Now, real quick, by the way, shoot, I set this up wrong to make you suck, Jeff. All right, let me do another one of these. Yeah, that's perfect. That's fine. Okay, yeah, because I don't want to do on some gross stuff. Okay, here we go. Oh, has everybody got this one? Before I erase it, okay. Let's do one with a little bit nicer numbers, and then I can actually connect it to what we're doing over there. We ask people how many TVs they have in their house, let's say. No, let's make it really nice, Jeff. 0.1, 0.5, 0.2, 0.2, I think, right? Yeah. Okay. So 50% say they have one TV, 10% have no TVs, 20% have two, 20% have three. Okay, I like it. So can somebody tell me what's the probability somebody has 2 TVs?
20%.
Right, don't overthink it. What is it? 20%, right? So for some reason, I always have somebody who's not able to read this. But the probability to have 2 TVs is 20%. The probability to have 1 TV is 50%, so forth, right? So that's a pretty nice, easy question. What's the probability that somebody has at least 1 TV? You can do that 2 different ways. What do these probabilities all add up to be?
1.
They all have to be 1. The probability that somebody has at least 1 TV, you can either add these up. Don't all of these add up to be 1? Right? Right? Okay. So if I want to know the probability of these, couldn't I just do 1 minus the one I'm leaving out? The probability of at least 1 is 1 minus the probability of none. That's what we said earlier. So again, just the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3 equals 1. So what's the probability of at least 1? Just going to say at least 1 is 1 minus probability of none. Again, hopefully that makes more sense. Since they all add up to be 1, to find one chunk, I give you 1 minus the other chunk. Either way you do it, you get frickin' 0.9, yes? Okay, maybe. Now, remind me, what did we learn in chapter 2? We learned the 2 most important things to calculate given a list of data. One of those was the average, and the other one is everybody's favorite. So one is where's the center, and the other one is how spread out the data is. So one is the average, and the other one is the standard deviation. So no matter what way they give me the data, I want to know how to calculate 2 things. The mean. Okay, now we know how to figure out the mean. We got a formula for it. There's the formula for the mean. If they give it to me like this. We also want to know what's the formula for the standard deviation. How much time do I have? Not much. Now, real quick, I want to show you something. I'll show you this, and then I'll try to figure out how much further I want to go. And you're all like, "Oh, you can stop now, Jeff." Be quiet. What was the formula for the mean before?
Sum of x over n.
Yeah, sum of x over n, right? Good old add them up, divide by min, right? Right. We just created a new formula, but it was based on this, correct? So the new formula, it's really just the formula we use if they give it to us in a table. Can somebody remind me what's in the bottom of any probability? What was it? The probability of something is the number that match what I'm looking for divided by the total number of things, yes? So isn't this built in to this? Aren't these the same frickin' formula? Doesn't this have an over n in it? Isn't the probability over n over the total number of things? And again, what I'm saying right now, if you don't quite get it, it's not absolutely important. But I want to point out how all these frickin' formulas really are the same formula. They just kind of look different based on what they tell me. Maybe. So what we need to do is we need to figure out how is this formula going to change? Remember this good old formula? Yay! That one's going to take, let me do one piece of it, and then we'll call it a day, okay? Because I feel like I've thrown a lot at you. Okay? We have a lot to catch up with, and I want to get a little bit in the fore. This is actually a really good place. Let me do a little bit of the, well, shit. Yeah, okay. So if I'm given this, I will do this, and then this will lead me to the mean, correct? You see how instead of adding the x's and dividing by n, I multiply the x's by p of x and then I add those up because the over n is built in. So watch this. Normally, wouldn't we have done this next if it was a normal list of data? Remember calculating the standard deviation, I have to get a table of these so I can add them up and divide by n? You guys semi-remember that? I know it's been like 2 weeks. So watch this. Instead of doing that, we do exactly what we did here. Instead of adding these up and dividing by n, I multiply these by p of x. The same exact way. Instead of adding x's up and dividing by n, I multiply them by p of x and add those up. Because the p of x has an over n in it. Instead of adding those up and dividing by n, I multiply those by p of x and add those up. Because the p of x has an over n in it. So the one little thing I want to do is if I look at this, the sum, let's see, Jeff, do you want to do this? So let me stop here. This is the official technical formula for calculating the standard deviation if they give me x p of x shit. This formula sucks. There's a lot of work to do in this formula. There's a quicker way to do this, and it involves some algebra to rewrite this formula in a better way. But I'm not going to try to cram that in at the end. I think we'll stop there. Right, that's plenty. You guys look really depressed, I'm sorry. You know, like, yay, Jeff is back. Yay. Okay. So next time, I'll have a handout related to chapter 4. We'll kind of work on that. I'll finish up the standard deviation kind of stuff. And of course, the very first thing we're going to do is the quiz on Thursday. So, and again, just to remind you guys, I'm in here at 8:30, unless the printer gives me trouble, and then I'm in here about 8:35. If you want to come early and ask questions. Okay. If you didn't get your test back, come up and get that back.